Hey gang, this is the first sort of flip video here in our crazy Corona times. Just wanted to do a chapter 16 kind of catch up, just to kind of see where everybody is. It'd be good if I spelled the word catch correctly, I suspect. So just trying to go over some of the topics that I think are pretty important from chapter 16 that you should know and you should remember. Of course, A period and a few other people took the quiz, and then school got scuttled, and so we've got this weird little S day, but I don't think it's worth trying to do a quiz at this point. For those of you that took it, we'll just figure out what to do about that, but I'm not too stressed about it, and you shouldn't be either. There's kind of bigger fish to fry in the world right now. So let me just go over a couple of the things that I really want to make sure that we are aware of and know what to do with. The first of which simply is what to do, how to handle, how to understand if you have any kind of weak acid or base or their conjugates, because their conjugates are really just the same thing. They're actually just weak acids and bases themselves. And if they're by themselves, then the way to deal with them is really simple. And the concept really is that the weak acid, let's call it HA, as is often the case, when added to water, which is known as a pure liquid, and everything else in here is going to be aqueous, you get H3O plus and A minus, which is again that conjugate base. That means the Ka expression is simply hydronium times A minus, the conjugate base, all over HA. And that expression is unbelievably versatile and really useful, as we'll talk about in a little bit. But because this thing is just all by itself, HA, is all by itself. That means that you're going to get equal amounts of H3O plus and A minus. They're going to be in exactly equal amounts because every time HA breaks up, it makes one H3O plus and one A minus, or 7 H3O pluses and 7 A minuses. There's no reason why they would ever not be exactly the same in a solution of just HA. And so because we're talking about this situation where they're just by themselves, that means that H3O plus will equal A minus, and that's where we get that sort of familiar abbreviated form that Ka is simply going to equal x squared over that initial molarity of HA minus x, because that molarity does go down by a little bit as it produces H3O plus and A minus. So a fairly easy thing to deal with there. It works exactly the same way for bases. So if you have a weak base, which the College Board labels it B, again, water, the only liquid in here, everything else being aqueous, we're going to get OH minus and HB plus, which is the conjugate acid. And Kb then equals OH minus times HB plus all over B, the base, not boron. And yet again, because we're talking about a weak base all by itself, whenever it breaks down, you get exactly the same number of OH minuses and HB pluses. They're going to be 100% identical every single time when you have B by itself. And so OH minus hydroxide is going to equal HB plus, the conjugate base, the conjugate acid. They're exactly equal. And so once again, we get this familiar x squared over the molarity minus x situation. So very easy to deal with there. So that happens again if I have a weak acid or a base, and I think what maybe gets lost a little bit is that it also happens if we have a conjugate of a weak acid or base, because a conjugate of a weak acid or base is itself a weak acid or base. So the math works out exactly the same. Maybe it doesn't seem like it does. There's sort of this, well, what's this other ion, like sodium or potassium or something thrown in there? It doesn't matter that it's there. Because it's always going to be soluble in water, never going to stick to anything, and doesn't affect anything. So if, for example, we have a situation where you have something like, the cyanide ion, let's say it's from sodium cyanide, well, the sodium in there doesn't matter, right? It's always going to be an A plus, not doing anything in water. So all we're really worried about is the Cn minus. Cn minus in water, even if you were a little bit uncertain, like, oh, is that a conjugate acid or base? Where does it come from? I don't really know. That's fine. there's two ways to know. One, they would give you that HCN as a weak acid. They would give you the Ka for HCN. So they would certainly give you some indication that because HCN is a weak acid, you could probably figure out that CN minus must be its conjugate base. But also, what in water is it going to be attracted to? Well, it's incredibly negative. So what part of water would it be attracted to? Of course, it'd be attracted to the positive part of water. So we would get, it sticking to the H plus part of water. When it pulls H plus out of water, it leaves OH minus behind and turns itself into HCN. And that may not resemble at first what we just talked about, but it actually is the same idea as B plus H2O makes OH minus and HB plus, where B is CN minus and HB plus would thus be HCN. So it's exactly the same thing as what we've talked about before. So there's nothing different between any of these weak acids or bases and their conjugates in terms of how you approach them. The only difference, of course, is that the K values would be different. So the KB value here would be equal to KW over Ka for HCN, which is its conjugate. And so that would obviously be given or have to be given to you. Again, now we don't have to worry about it too much because it's not going to be given to us in this particular setting because it looks like the College Board is not going to ask questions about these kinds of things. So, woohoo, we're home free. The other important idea from chapter 16, which goes a little bit into chapter 17, is this concept of the common ion effect, which simply is the idea that if you have a mixture of conjugates, what that does to the pH of a system. And we'll talk about that a little bit more when we start into chapter 17. But essentially the idea is that the conjugate pair is, I guess both of them have a source of the same ion. So the idea then is that that ion is common to both of them. So the idea, for instance, if I have something like HCN and NaCN, they can both produce CN minus. Now they don't both produce it at the same rate, but that's where Ka for HCN and Kb for CN minus come into play. And in these circumstances, and this is where it gets different because now, of course, we have two different things and not just HCN or CN minus by themselves, but we have them together. And because we have them together, there's no guarantee that H3O plus and CN minus are going to be the same, or that HCN and OH minus are going to be the same. So once we know that, then we have to kind of think about the bigger sort of idea of the usefulness of Ka or Kb, which we generated before. There's Ka, Kb looks very much the same, except that CN minus is sort of our focus, and so we have OH minus and HCN and CN minus. You can use those, either one of them. The key is simply that these two parts, the numerator, are not going to be equal. And because they're not going to be equal, you can't rely on this whole x squared over molarity minus x. In fact, all you really do is just plug in the values that you have. And yes, some of them are going to go up and down by x, but again, we're going to ignore that plus or minus x because the AP is not going to ask about this year anyway, because it's no longer part of the curriculum. It doesn't really matter, does it? As long as you simply know that that's what's going on. One of the things that we'll touch on in the next probably day or so, I would guess, would be the idea that when you have a mixture of those things, it creates what's called a buffer solution. So anytime you have a mixture of a conjugate pair, it's called a buffer. And we'll talk about why that is in a little bit more detail when we start into chapter 17, even though that just is sort of extra knowledge that makes you super smart. So. But I think that's pretty much it for chapter 16. Again, stuff that you don't fully need to know, but still good to know for you smart kids as you head into dominate your college classes.